So let's solve a different type of heat equation. So far, we've seen the one-dimensional heat equation. The one-dimensional heat equation is the heat equation given by the partial differential equation. The partial derivative with respect to t is some constant k times the second partial with respect to x. Here I'm assuming that the function u is a function of t and x. There's also a two-dimensional heat equation and a three-dimensional heat equation. The two-dimensional heat equation is the equation where I say the partial derivative with respect to time is some constant k times the second partials with respect to x and y added together. So instead of just having an x coordinate, I now have two spatial dimensions, x and y, and I'm assuming that my function u is a function of the three variables x, y, and t. You could generalize this to the three-dimensional heat equation, which is analogous. It's the partial with respect to t is some constant times the three partials uxx plus uyy plus uzz. I'd like to look more closely at the two-dimensional heat equation after a long time. So what happens if I look at the following problem? I have a metal plate, let's say a metal plate that's in the shape of a rectangle. So I have a metal plate, and I guess the width of the plate is L. So the x spatial dimension will go from 0 to L, and the height is h. If I keep the temperatures around the outside edge some constant temperature, then eventually, after a very long time, the heat in the middle will stay constant. That's the steady state heat equation. So if I want to solve the heat equation on the two dimensions, like I've shown here, and I wait a very long time for the partial derivative with respect to time to stop changing, then we get this equation you see in the first row. This is the steady state heat equation. The conditions here say the following. If I look at the coordinate by taking x equals 0 and y to be anything, then I'm holding the temperature constant at 0, meaning that this side of the plate is 0. If I look at the right side of the plate, if x is equal to L, it doesn't matter the y variable, I always get a temperature of 0. So I'm holding the two horizontal sides constant at 0. The base of this triangle is also 0 degrees, but I'm letting the top of this rectangle have a varying temperature given by some function f of x, which I'm depicting here, meaning this part of the rectangle could be heated up, maybe this middle part be cooled, and this other part heated up as well. Then, if I wait a very long time, what will the internal temperature be? So if I have an x and y coordinate, if I wait a long time, holding these three sides at 0 degrees and the top at some varying temperature, what will this coordinate's temperature be if I wait 5,000 years? That's the physical interpretation of this problem. So I could solve this steady state heat problem in the same way that we solved the one-dimensional heat equation. We could start by assuming that my solution can be written as some function of x times some function of y. Then what this assumption allows us to do is take partial derivatives very easily. If I look at this steady state heat equation, then the second partial derivatives give me x double prime y plus x y double prime should equal 0. So I could separate the variables. I could put all the x's on one side of the equation, all the little y's on the other side of the equation. If I do that, I'll get x double prime over x is equal to negative y double prime over y. Now I've separated the variables. So on the left side of the equation, I have a function of x. On the right side, I have a function of y. And the only way a function of x and a function of y can be equal is if no x's and y's explicitly appear in the function, meaning the function has to be a constant, which we will call negative lambda. This gives rise to two ordinary differential equations. We have equation 1, which I'll write down in the x equation, is x double prime is negative lambda x, subject to the initial conditions that if I plug in 0 or L, I get out 0. So x of 0 is 0. X of L is 0. We've already solved this differential equation. So before I write down the second equation, maybe I should just write down the solutions, because in a previous video, we've already done the work for this. So solutions are, my function is some constant times sine n pi over Lx, and that only happens when this constant lambda is positive and given by something of the form n pi over L squared, where n is a non-negative integer. So we've done that work before, so I already know the solution. Now I could write down equation 2 involving y. Now there's an extra negative sign in this problem, so the second differential equation is y double prime is equal to positive lambda y, subject to the constraint. Now I'm only going to use the first constraint here, and then I'll save this constraint later for when I want to find the coefficients in my big sum. So I'm only going to focus on this 0 constant and say that I get y of 0 is equal to 0. I already know what lambda has to be. Lambda has to be positive, so I don't need to break this problem into 3 cases like I did when I first solved the other problem. I already know lambda's this constant. So solutions are my function y, which is some constant c1 times e to the square root of lambda y plus c2 e to the negative square root of lambda y. Again, I know what lambda is. It's this constant, but that's kind of a big thing to write, so I'm just keeping it as lambda for now, but I am using the fact that I do know lambda is positive. Now I will use this condition that if I plug in 0 for y, I should get out 0. So if I plug in 0 for y, I get c1 plus c2. So that was found by plugging in 0 for y and setting equaling 0. So that means I know c2 is negative c1. So I can use that in my function here, and I get y is really c1 times e to the square root of lambda y minus e to the negative square root of lambda y. Now, I can multiply this by 2 and divide by 2. And the reason I do that is because the solutions can be written in the following form. This term right here, inside this parentheses, has a special name. It's really hyperbolic sign, sinh. So it's sinh, the square root of lambda y. If you don't like that, if you've never seen that before, it's just a definition, so there's nothing to worry about. The definition of sinh is exactly this. So instead of writing a bunch of e's and a subtraction and division by 2, I'm just going to abbreviate that whole thing with the hyperbolic sine function. Okay, so now I know x, I know y. Therefore, I know the product, x times y. I could write down my general solution for u and almost be done. So thus, the function u of x and y is an infinite sum. So I have an infinite number of solutions, one for each positive integer value of n. So I'm going to have the sum, n going from 1 to infinity. Then I have some constants, I'll call them bn. I have my x solution, which I guess I'll write first, sine n pi over L x. Then I'm going to multiply that with my y solution, which is hyperbolic sine, sinh, of another n pi over L y. So this is my general solution to the steady state heat equation with the constants there. I could find the constants using this final condition I haven't employed yet. It says if I plug in y equals h, I should get out my function f. So my function f of x is the sum, n going from 1 to infinity, bn sine n pi over L x, and then this will become hyperbolic sine, sinh, of n pi over L times h. This is some constant, just like bn is a constant. So I could use the pairwise orthogonal property of the sine function on the interval from 0 to L to get that bn times sinh n pi over LH should be the projection of f onto the orthogonal family of sine functions. So that should be the inner product of f with sine n pi over Lx divided by the inner product of sine with itself. I'd like to know the constants bn. This is just some constant, so thus I'm done with the problem once I write down the constants bn are given by 2 over sinh n pi over LH times L, again using the fact that this term here is equal to L over 2, that's why I get the 2 over L, times the integral from 0 to L, this inner product being f of x times sine n pi over Lx dx. So I have my constants that I could place right here, and I get an expression for the solution to the steady state heat problem. Okay, I think I'll use the software Mathematica to visualize this and the previous problems that we've solved using the heat equation in the next video. Please follow me along there.